the director of the National Institutes of Health, and as this slide indicates, he's a risk taker. He's an awardee and an advisor to President Obama, and of course, everybody knows that he's a rock star. Francis.
Well, thank you, Jeff. I think it's wonderful to be able to be here in a room full of such international expertise in this area of genomic medicine. And much thanks to Jeff and Terry, who have labored over many weeks and months to try to bring us all here together for what I think is going to be a memorable couple of days. And certainly like to add my exhortations to those you've already heard from Jeff about the importance of making the most of this opportunity to try to come up with concrete recommendations about how, on the international stage, genomic medicine can move forward at this propitious time where so many opportunities are emerging, but there are many obstacles as well that may slow or impede their implementation. And I think if this group in this room can't identify how to move forward on this, then I don't know who could. So I hope everybody will go forward over the next couple of days very much with that attitude and intention. In my brief 15 minutes, I just thought I'd set a very broad set of perspectives about where we are now with genomic medicine and a little bit about where it's going. Much of this will be familiar to most of you, but perhaps not all. Certainly from NIH's perspective, the focus on the use of genomics to advance human medicine is a compelling one. It fits nicely within our mission, which is both about fundamental knowledge acquisition and also about the application of that. And certainly the fundamental aspects of genomics are breathtaking in their sweep practically every day. I have some experience of hearing about some use of genomics to understand basics of development or some other aspect of human biology that you can't imagine even a few years ago would have been possible, and yet these things are happening all around us. The application of that knowledge to bring this to the clinic is the main topic we're going to be focused on here for these couple of days, and is obviously a complex issue with many steps involved. The Human Genome Project was a bold enterprise when it started in 1990. Many people who weren't around at that point may have a hard time imagining that this was a very controversial effort that quite a significant fraction of the scientific community was opposed to, in part because of its technical challenges, in part because of concerns about cost, in part because of concern that it might be so boring that nobody would want to work on it. I'm glad to say that didn't turn out to be the case. And instead, some of the best and brightest people from all over the world rolled up their sleeves, got engaged in this in an unprecedented team effort for biology, ultimately involving about 2,400 scientists from 6 countries, revealing then in 2003 the essentially finished version of a reference human genome, something which we thought at the time was pretty impressive, but now when you look across the world and see hundreds of thousands of human genomes being produced by people representing organizations in this room, it is amazing to see how far we have come. The challenge, of course, is to take that information and help these people here at the bedside, and you can see this doesn't look like a particularly happy interaction. Staring at nucleotides and one of the docs at the bedside, I don't know what to do, what do you think? So we clearly got to get beyond that image into something else. And obviously the genome sequence alone did not provide the kind of insights that one needs to make this encounter go better. And even before the Genome Project had completed its original goals, other things sprung up. The HapMap project, also a very important international effort to catalog human variation. The subsequent 1,000 genomes effort to try to expand that catalog even more deeply by carrying out extensive sequencing. The focus on cancer, which I'm sure will be talked about at this meeting, because in many ways cancer represents the leading edge of genomic medicine, since cancer is a disease of the genome, and discovering actionable findings in tumors is now becoming a very compelling clinical application. The ENCODE project, which aims to try to understand how the genome actually functions and has provided public information that certainly my laboratory uses every day to try to understand how it is that variations in non-coding regions affect the way in which the genome functions. So all of those databases happily now placed into the public domain immediately upon deriving the information, which is an ethic that I think the genomics field has pioneered and which is now spreading into other aspects of medical research, has made it possible for individuals, even with modest resources, to tackle really hard problems that might not have been approachable even a few years ago. One consequence of the HapMap project and then the use of that catalog of variation by large numbers of groups who have been studying common diseases over the course of many years is the possibility, by doing association studies, to identify variations which at very high statistical confidence are associated with disease risk. The catalog that is kept up by NHGRI, represented here in this diagram, has now identified or brought together information that has been identified by groups all over the world, representing an amazing harvest of information about the risk factors for common disease. Each one of these colored circles representing a variant that has been statistically at high confidence associated with a particular disease, providing insights into pathogenesis of disease that are really quite striking. Even though most of these genetic variants carry a very modest odds ratio, they're still teaching us something pretty exciting about pathogenesis. And meanwhile, the cost of sequencing the human genome has been falling dramatically, as you all know. This diagram, which is one that everybody likes to show, but maybe have different versions of it, showing on a log scale the drop in cost for sequencing a genome from roughly $100 million US down now to the estimate I just got from NHGRI, about $5,000 for a complete sequence as of the end of 2013. And along with that, advances in the technology that have made this possible, taking us from sequencing instruments the size of phone booths to some of them at least that are actually quite micro-scaled and are capable of generating a huge amount of data in a short period of time. That, of course, now makes it possible to apply the sequencing approach to try to understand the cause of a disorder that may previously have been utterly mysterious. And I think all of us are finding this to be quite exciting in terms of applying whole genome or whole exome sequencing to understand the mysteries of particular rare diseases. An example that is allowing us to build this catalog of disorders with known molecular basis at a prodigious rate, and I suspect this diagram, which was already going up pretty fast, will bump up even faster in the next year or two because of the ability through sequencing, even in families where there are relatively few individuals affected, maybe even just one, to come up with the actual causative mutation. In some instances, that itself can lead to dramatic medical benefit, and we all have our favorite examples. Maybe one of my favorites is the Beery twins, and if you go to the Smithsonian and look at one part of the exhibit, you'll see a little bit more about their story. These twins, fraternal obviously, diagnosed with cerebral palsy at age 2, but their diagnosis didn't really fit because they began to progress. The mother questioned whether these symptoms were right, sought a new diagnosis. There was a tentative sort of clinical diagnosis of dystonia. There was some benefit from L-DOPA, but by the time these twins were getting older, health was deteriorating severely, and particularly the girl, Alexis, appeared to be on a really downhill slope that was not going to have a pretty outcome in the near future. So what happened? Genome sequencing was carried out. They discovered in this pair of twins a new genetic disease, basically, that affected both the metabolism of L-DOPA but also of serotonin. And by adding to this the diet, not only L-DOPA as a drug, but also 5-hydroxytryptamine, they were able to get beyond the block that was causing their serious neurotransmitter deficiency. And as you can see from this still photo, here they are dancing on jumping on the trampoline. We featured this family actually a year ago in a celebration of science that we had at NIH. Those are Alexis and Noah with their unaffected sibling brother standing between them. So those stories are indeed inspiring, and I could tell you about another dozen or so if we had time. But of course, most of those are the exceptions. How are we doing, though, in terms of using DNA sequencing to at least get a diagnosis? We wanted to push that forward. At NIH, the Undiagnosed Diseases program, launched in 2008, has been not only through exome sequencing, but a wide variety of other kinds of medical evaluations, trying to see if we can come up with diagnoses for patients who have long-standing medical problems that have eluded a diagnosis. Bill Gall, who leads this, and his team of about 30 physicians have evaluated about 3,000 cases, accepted about 700 of them for evaluation, and carried out in all instances extensive analyses that involve scans and physical exams and other things, but also include exome sequencing, and have managed to come up with a diagnosis in about 25% and identified a couple dozen of new diseases that were never previously described. This has gotten a fair amount of press attention because of the mystery that this represents, sort of a real detective story. And we have now implemented a new version of this that stretches the Undiagnosed Diseases program across the country. This is funded through the NIH Common Fund over 7 years, $145 million. Harvard will serve as the coordinating center, and there will be 5 to 7 sites added this summer, again, to try to use some of these tools to come up with answers to vexing problems, most of them for very rare conditions. So the good news is that we're doing better at finding the causes of disease. The bad news is we have not been doing so well in terms of identifying therapeutics, and this has got to be a major focus of anybody who cares about genomic medicine, is this huge gap between our ability to diagnose and our ability to treat. Here at NIH, focusing on that, we have identified or developed an entirely new center, the National Center for Advancing Translational Sciences, or NCATS. And one program that is modest in size, but I think potentially large in impact, is this one called Trend Therapeutics for Rare and Neglected Diseases, which aims to try to fill in what is otherwise that dreadful valley of death, where discoveries about cause don't find their way to therapeutics because of all the barriers that occur there. And I could cite you examples from that for conditions like sickle cell disease or some rare conditions like Niemann-Pick, where we have made substantial advances through this kind of capability. And certainly in other countries, similar things are being tried. We're also using, through NCATS, the ability to collaborate with pharmaceutical companies to try to see whether there are existing molecules that have been tried for some purpose and actually failed on the basis of lack of efficacy, but might be just the thing for a rare disease that has currently no available therapy. This has now led to a partnership with pharmaceutical companies where compounds are being made available for investigators to try for different applications. And we have some exciting things beginning to emerge there. And also trying to speed up the process of how you go from a good idea about a therapeutic to an actual successful application by speeding up toxicity and using some high-tech efforts with our colleagues at DARPA, which is part of the Department of Defense, to be able to develop human biochips to test toxicity instead of using animal models. Finally, though, let me say the science, as wonderful as it is, if we're really interested in clinical benefits, has to be connected clearly with the connection of understanding how to achieve the right kind of ethical principles and the right government policies. If you go across to the Jefferson Memorial, although it's a little chilly to do that today, you will see this quote on the wall inside the Jefferson Memorial from Thomas Jefferson: "Our laws and institutions must go hand in hand with progress of the human mind." How are we doing on that? Well, actually, there's a lot to be said about that. Certainly the laws that relate to patenting of human genes have had an interesting year over 2013. This major legal decision in the United States where the U.S. Supreme Court ruled that patents that had been issued to Myriad for BRCA1 and BRCA2 were in fact things that should not have been allowed, ruling that these basically are genes in their natural state and therefore should not have been patentable under our Section 101. Regulatory challenges obviously play a huge role in terms of advances in genomic medicine. I'm sure that will get talked about at the course of this meeting. You may have noted just a couple of months ago, our U.S. FDA announced the first regulatory clearance of a sequencing device, basically clearing the path to having that device used to generate data that FDA would consider useful, both in terms of companion diagnostics and other things. In this case, the broad clinical use is for the Illumina MiSeq instrument. And of course, there are many applications that you can contemplate would be enhanced by having this kind of FDA green light. Peggy Hamburg and I wrote a brief perspective about this in the New England Journal a month ago, which you're certainly encouraged to look at if you want to see a little more speculation about where FDA thinks this is going and where NIH would like to see it go. Obviously, not everything has gone well and easily. The other thing that happened about a week after that was FDA sending a warning letter to 23andMe, a company in the United States that offers direct-to-consumer DNA testing, saying that they should cease to market their efforts until they've answered some questions about the scientific evidence upon which their particular product is based. And we're all waiting to sort of see how that shapes out. But again, there have been noises that perhaps something like this was going to happen, and now it has. Certainly, to conclude, in terms of policy considerations, we have to be mindful of, while there are many benefits of genomic medicine to the individuals, there can also be potential harms if we don't provide the appropriate protections. Some of us started working in about 1995 on the need for, in the United States, legislation that would prevent genetic discrimination in access to health care and in employment. And that, after a very long number of ups and downs and twists and turns, ultimately was signed by President Bush in 2008, the Genetic Information Non-Discrimination Act, which does say you may not have genetic information used against you in health coverage or in the workplace. Other things you might want to notice that are in the works, there is an expanded genomic data sharing policy, which is under consideration in the U.S., which was put out for public comment a few months ago. Those comments have been received, and we're in the process of sifting through them. Certainly, the idea here is to promote sharing by making data accessible to qualified investigators while still maintaining sufficient protections about privacy and confidentiality. And on a broader scale, the so-called common rule, which guides human subjects research in the United States across many different agencies, is under serious consideration for modifications to try to both increase protection for participants against disclosure of identity, but also to decrease the unnecessary burdens on research which have crept in and which actually threaten to completely make certain aspects of clinical research almost untenable because of the amount of bureaucracy and unnecessary attention to details for projects that are very low risk. This is also something to watch closely. And of course, we are talking about genomic information. The idea that you're going to sequence someone's genome carries with it inevitably the fact that you're going to discover things that were not expected and that that person may not necessarily want to know, or maybe they do. So the whole question of incidental findings is a critical policy ethical question. And there's just been a recent report by the Presidential Commission for the Study of Bioethical Issues on this topic that you're encouraged to have a look at. So finally, again, I'm glad we're having this conversation on the international stage because certainly the human genome is our shared inheritance. If we're going to advance the use of that information for the practice of medicine, it should certainly never be done in a narrow way. Louis Pasteur knew this: science knows no country because knowledge belongs to humanity and is the torch which illuminates the world. I think genomics could very well line up behind a bunch of other torches, and it's my hope that in the course of this meeting we will figure out how to make that all come true. So thank you very much for your attention, and I'm delighted to be part of this really landmark meeting here in Washington.